Elliot, do you want to give a brief introduction about yourself?
Yes. Let me also move the pictures of everybody over here to my second monitor. So I'm Elliot. I've been programming since high school, which is to say like 2005-ish, I think I started. And I got interested in functional programming around then. And I've been using functional programming professionally basically since I've graduated. I've managed to find positions mostly using Scala, which is a functional programming language. Today for this, I thought I would actually do this in Haskell, because I think that the syntax of it really kind of makes some of the stuff a bit more obvious and kind of easier to see, I think. So if you don't understand something, please stop me and have me dive into it, because someone else probably could also use the clarification. So to start out with Haskell Syntax, kind of the most basic thing in it. Oh, it looks like we've got Tyler now, which is good.
Hello.
Great. So as I was saying, I'm going to do this actually in Haskell, since I think that the syntax of it will help make some of the stuff a bit more clear. So to start off with Haskell syntax, function application in most languages, you write something like f of x, y, z, right? In like C, for example. In Haskell, we instead say f of x, y, z. So its function application is just spaces. And additionally, so in C, you might have f of x, g of y, where you're passing the result of g of y into f along with x. In Haskell, the way that you would say that same thing is f. So just like in math, you use parentheses for grouping expressions. So it's the notation of using spaces instead of parentheses is also something that you see in some places in math. And Haskell borrows that set of syntax that you'll see in a few places in math. So recursion. The basic thing that recursion is explaining something in terms of a simpler version of itself, is the simple way of putting it. And there are two main types of recursion. There's structural recursion, where when you're calculating something, you just work on the recursive structure of something. And then there's generative recursion, which is where you transform something into a recursive form. And I'm going to ignore that because it's more complicated, and also most things that you'll, the simpler things are structurally recursive, and most things that you'll have to do recursively are structurally recursive. So to start out with, what's a really simple example of something that is structurally recursive? So one thing that you can kind of see as being structurally recursive are numbers. And so like if you look at 5, or 6, those don't really look like they're structurally recursive, right? But you can kind of see 6 as being 5 plus 1, and 5 as being 4 plus 1. And similarly, 6 is like that. And, you know, you can go more layers of peeling off this unary encoding, right? Yeah, and that's 6 there. And we can actually get rid of this last parentheses because that's redundant. And actually in 18 something or other, a guy figured out how to do math this way. Giuseppe Pino, his name was, and he did all of math basically in terms of unary, and just if you define numbers as like a number is either 0 or a number is 1 plus some other number, you can define addition and multiplication and everything quite nicely. So let's take a look at that. So to start out with, let's make a data type. So in Haskell, we can introduce new data types using this handy dandy data keyword. And so we'll say data I, because int and integer are taken. So one of our new integer things, it's either 0 or it's plus 1 of a number. And so basically what this is if we had in, say, Java, it's similar to having like abstract class I, and then you'd have class 0 extends I, and then class plus 1 extends I, and then in your public plus 1, you'd have your like inner so you'd have a constructor that takes a plus, or not a plus 1 in I, that the plus 1 is wrapping. So so we can say, for example, here that we have like 0 is 0, and then 1 is plus 1 of 0, and 2 is plus 1 of 1, or equivalently, plus 1 of plus 1 of 0. So we're kind of like counting in unary, if that makes sense. So let me save this and reload. And then the other thing that I should probably say here is this. So that way if I type in 0 there, it'll print. Otherwise, Not everything in Haskell can be displayed, like functions can't be displayed, for example. So you don't really have to worry about that deriving thing there. So suppose that we want to add together two of these numbers. We would want to say add, and so we're taking in two numbers. So we have x and y, and we want this to be x plus y, right? So what we can do in Haskell is actually pattern match, it's called, on the arguments. So when we define a function like this, we can take one of our arguments, say, and we can kind of come at this case-wise. And what this basically is, and something like Python is, it's like saying def add x, y, and then if, in Python is it is type of or whatever to get the class something is, something like that. So you'd have like if y is type of 0 dot dot dot, if y is type of +1 dot dot dot, where I don't remember the syntax in Python for actually doing that, but it's basically like having a if at the top level of your function. And you can also kind of destructure it. So here, when we say +1 y, that y there is kind of the inner number that we've pattern matched on. Rather, that is in the constructor here, sorry. So if you want to add 0 to anything, the what you get back from x plus 0 is going to just be x, right? Everyone will agree with that? And then this right here is somewhat interesting. If we want to add 1 plus y to x, what we can do is say that this is +1 add x, y. So basically, so x plus y plus 1 equals 1 plus x plus y, right? And so let's load that in, make sure that I didn't. So let's see, add 0, 0. So that tells us that adding 0 and 0 is 0. Then we can say like add 2 and 2. And did I make a mistake here? Apparently, because that is hanging on that. the hell? Okay, that's odd. Sorry.
This is what you get for doing it live versus sticking to your slides.
Yeah. And I had written the code earlier and I had tested it and I didn't run into this. And this is incredibly bizarre. And okay, so the issue is somewhere with like the definition of 2. Oh, I'm an idiot. Do you see what I did here? Okay, oops. Okay, so what I did is instead of saying that 0 is this 0 constructor for I, it's 0 was just the infinite loop of like saying x equals x. So I'm an idiot. At any rate, so sometimes what people will talk about in terms of like understanding recursion is following down the like stack and that sort of thing. But one of the cool things about Haskell is because it is a pure functional programming language, we can actually reason about it equationally. So let's do an example of that. So let's say that we have add 2, 2. So what does this equal? So we can just apply this. So we'd have +1 of add. This is 1. And I will use these simpler things from here. So add 1. Actually, no, it's 2 because of x there. And then 1. And then we can do that again. It's +1 of +1 of add to 0. And then this, we can then apply this part of it to say that this is +1 of +1 of 2. So just kind of like brute force taking the definition there and using it. So the question now is, where did I lose people in that explanation? Because I guarantee that I lost at least one of you at some point. and something doesn't quite make sense to you. I would like to clear things up before continuing for anything that people don't quite understand. Anything?
I think I get it.
Okay. And if the dog, who I guess finished that one shoe already, will move over to the side here. I can keep on going. So let's write another useful thing. Let's say that we want to take a regular number and convert it to one of these things. So we have 2i of, so actually let me introduce Haskell type signatures. So you want to write something like this. So what this says is you want to write something that has type int to I. So a function that takes an int and returns something of this type I. So we have 2i of x, and like we're kind of stuck here, right? So what we can do is, let's say that 2i of 0 is 0. So kind of like that very basic case analysis. It's our base case. You'll also hear it called. And then we have 2i of x is 1 plus 2i of x minus 1. And this is partial, so it'll only work for positive numbers, which are the only ones that we're actually considering with I here. So I suppose we could have called it like counting number or something like that. So again, so let's write that, reload this here. Oh, sorry. It's mixing up these things. So it's plus 1 of our 2i on 1 less than the number. So this is basically saying that if we have like 5, so we have, actually, let's go through this again. So we have 2i of 5, right? So this is plus 1. Actually, let's make it simple, 2. So this is plus 1 of 2i of 2 minus 1, which is to say 1, which is plus 1 of 2, so plus 1 of 2i of 1 minus 1, so 0. And that would be the plus 1 of plus 1 of 0. So it's, so I mean, again, it's basically, we're taking our number x, and then we're writing this in terms of x minus 1. And because we've handled the x minus 1 case and the 0 case, this is kind of inherently complete for positive numbers. And kind of the nice thing about this is you can just kind of look at it and you can see that we have correctly implemented the +1 case and correctly implemented the 0 case. And as long as you're sure that both of those cases are correct in general, then you know that this whole thing is correct. And you don't necessarily need to think about like, okay, so what would this be if we had like 2i of 1,000,000? Let me go down the stack for each one of them. It's if you can do the case analysis and each of the cases is correct, then the entire thing when you compose it is going to be correct. And you can reason about this case-wise, which is nice. So let's do something like multiplication. So we have times. So this is going to be a function that takes in 2 of our i's and returns an I. And this is kind of the funny syntax in Haskell for writing that for some reasons that I won't really get into. So if we have times xy, what is kind of the easiest algorithm that people tell you for multiplication in elementary school or kindergarten? Lois or anyone?
What you're saying, like 1 times 1 kind of thing?
Well, so if you have like n times n, how do they like tell you to understand that?
It's just addition n times.
Exactly. So what we could say is if we have times of x and 0, we're adding x together 0 times, which is 0. And then if we have times x, and then it's 1 plus y. So this here is x times y plus 1, which, so this is equal mathematically to x plus x times y, right? So with the repeated addition, we can say that we want to add x to, add x to times x and y, where it's the y there again because the we have the +1 constructor, so it's y plus 1 on this side of things. So that should work. And let's see. So if we have times 2, 2, so that's 4, right? So let's say that we wanted to do factorial.
You might want to do a different one than times 2, 2, right? You might want to do times 2, 3.
Fair enough. So let's say here that we have 3 is +1 of 2, And find a few more of these. And this here would be an infinite loop. And then let's also say that we have the ability to call equals on these. So now, if we do that, and we have times 2, 3. So we have that, and we can say that equals 6, and that should be true. And also that times 3, 2, and times 2, 3 are the same. So that's pretty nice, right? So another kind of basic one that people will often use as an example here is factorial. And so n factorial is 1 times 2 times 3 to n, right? So we have factorial of 0 is defined to be 1. And then factorial of so 1 plus n, that's going to be times, we have this one n, and I mistyped that there because of Rebel. So plus 1n, and then we have the factorial of n, because we know that factorial of n is a way to calculate factorial on n minus 1, assuming that all of our cases are there. So we can kind of use the power of positive thinking to just kind of assume that we can solve this problem. It's very, very similar to mathematical induction, which I think basically everybody had seen in high school. It's, you just kind of solve the problem on your base case and your x plus 1 case, and assuming that you do that, because you can apply that x plus 1 case as many times as you need, it kind of explodes up to solving it for anything. Let's take a look at this here. So we have factorial of 1 is 1, 2 should be 2, 3 should be 1, 2, 3, 4, 5, 6, and then 4 is more than I really want to count there. But actually, let's see here. So 1, 2, 24. Yeah, which is right. So, so this is kind of the very simplest recursive thing that you might think about. And let me very quickly put the dog outside.
Bye, Rebel.
wants to be part of it.
That's right. He's so excited about recursion.
He is. He's such
He
a
wishes his dog food would recurse.
that he does.
Because he had dinner before this. He wants second dinner. And perhaps after that, maybe third dinner. And he thinks that because I don't want him barking during this, he can beg more. So does this here make sense to everybody as kind of like the most basic recursive way to write things? So the thing that you'll notice at each of these is that everything kind of had the same structure. We have our, we don't have any real structure left to write a leaf node, or we have some structure left. So you peel off a layer of structure, you fix it up somehow, and you use your operation on the smaller bit of what you're working on, and then you fix it up for the one greater, and use that. So does that make sense to people? I'm not losing anyone or going over people's heads.
You're good.
Good, because week 2, I had a couple of problems where I had gone a bit too fast. So hopefully I'm not going in the opposite direction of being way too basic and boring everybody. So let's take a look at a slightly more real example of a recursive structure, something that people probably have a bit of experience with, namely directory trees. So when you have a directory tree, at each layer in your directory, like you have a bunch of items in there, and some of them might be subdirectories. And actually, for now, I think just for making some stuff simpler, let's comment out symbolic links and just kind of look at it where you have either files or subdirectories. So there's a lot of things that you might want to do to a directory tree. For example, you might want to like see if a file is there. So let's have like a is there function, and that's going to take a directory tree and a path and return a Boolean for whether or not there's anything there, right? So we have is there, and we have our directory tree, and then so we're representing directory tree as a map from the name of things. So for example, in this thing here, you'd have keys like dist, new style, and recursion.cabal to the directory item, where the directory item is either it's a subdirectory that is a directory tree type, or it's a file that has a name and a size. And then so we have a path. So if we don't have any more path, then that represents, and the path is a list of strings. So that represents that we are in a folder. They're asking if that folder is there. So that would be true. And then we'd have is there of directory tree M, and then we'd have the next item followed by the rest. So this right here is kind of pattern matching on the list of the items in your path, or the names in your path. So that's the, so let's call this current and rest. So what is this going to be? So we have our map here. So let's get the item from the map. So this is going to be so case lookup cur in M of so this here is we are looking up the thing in the path to see if it's in there. And if it's not there, then obviously the item that we're looking for isn't there in this directory tree. Then if it is a file, so if it's a file, then we want to return if the rest of the path is empty, right? Which is basically like, if you're asking if there's like recursion.cabal/foo, and recursion.cabal is a file and not a folder, then recursion.cabal/foo doesn't exist. So that would be like rest equals the empty list, or is null empty list, or whatever. And then if it's just subdirectory of, so this is going to be, so we have a subdirectory, and then we have the rest of the items that we want to look up into it. And then we want to look up if that item exists in there. And luckily, there's a function that claims to be able to do that. Namely, it is the function that we are writing right now. So let's just call it here. So is there of subdir, and then rest. Let's see if, oh, that compiles. Oh, and yes, this is because I've wrapped path in there, and then we want to say gonna match expected type path. Oh. And then not much expected type. Oh, right. Okay. Great. So now, so does this look reasonable to you guys for finding whether or not something is in a directory? So what's some other things that we might do with the directory? So one thing that we might do is let's add together the size of everything in there. Because someone clicked on the thing in the Finder that's trying to find the size of the subdirectory there. So kind of at a basic level, how would you calculate the size of a directory? So the size of your directory is the size of everything, or all the files in that directory, plus the size of all of your subdirectories, right? So let's see. So what we'd want to do is so we can use the fold method that I was talking about earlier. Actually, wait. Actually, yeah, elms. Right. So this right here is going to get all of the items in the map. So it'll discard the file names because we don't really care about them in this case. And we can define a helper function called item size. So what item size is going to do is, so item size takes a directory item and returns its size. So item size, so it's either a file with some name and then a size, and that's just going to be the size of it. And then item size of a subdirectory. So here we have a directory tree, and then we need to get the size out of that. And fortunately, we're writing a function here that's able to do that. So we might as well do that. And then so now that we have that function, we can say something like actually here we can say sum of map item size over items. And what map does is it applies this function here to every element in there. So it'll take the list of the subdirectories and files at the current level of the tree, and it'll apply this item size function to it, giving us the size of our children and the size of the files in us. And then sum's, of course, going to add that together. And that should hopefully compile, except maybe a couple of minor compiler errors. Oh, right. Map.elms. And we'll get those types. So kind of again here, it's with recursive stuff, the most basic thing that you do is you have like your current level of structure, like you have your tree, and you solve it on your subtrees, just like you solved the problem on x minus 1, and then you fix it up. So in add size, you got the size of source of this dist new style and those subfolders, and then you added to it the size of my scratch file, setup.hs, changelog, directory tree main, and recursion.cabal. And then you return that fixed up version. And then at the higher level, the fixed up version is going to get passed back into the recursive call to the next higher level. And you can just kind of reason about these things at like the single case-wise level of like, have I handled the case of having a directory tree with some number of children, and have I handled the case of not having anything here, which in this case we're kind of inherently doing that because if we have a empty directory, then this right here isn't going to have anything in it, and that this is just going to be 0. So does that make sense to people? Because I see that we are coming up on about an hour, which is, I think, about what we wanted to do. So do people have questions? Do you feel like you understand recursion any better now?
From way back in college, I still had a pretty decent, or at least what I thought was a pretty decent idea of recursion. I'm thinking of the GIF where the person's mind is just blown, right? It's not completely blown, but it's definitely expanded and it's hurting a little. Thanks, Elliot.
Thanks. I figured just like really going with like the super basic, like Pinot arithmetic is kind of a good, like it's not the most practical thing in general, although there are places in programming that use Pinot arithmetic because it's convenient at a type level if you want to have like numbers in like generics. Kind of all you can really do is add on a type, basically. So there's a few places that that's used, but it's kind of the simplest thing there. Any other questions, Lois, Lana, Adam? Looks like at some point we lost Robert. So I guess we will call it then.
Thank you so much, Elliot.
Thanks, Elliot.
This was useful for people.
Oh, and you do have one more person than you thought you did.
Thank you, Elliot.
Oh, how are you doing?
I'm doing good.
What did you think of this? Did you learn something?
He only caught the end.
I only caught the
so-
end, but it was interesting looking, that's for sure.
Yes. So Lana had recorded it, so you should be able to get this up on YouTube. Can watch the beginning. It's
All right.
Very cool.
Yep.
We haven't talked about recursion yet, so.
No.
Yeah, it's recursion's really useful. It's when you're actually doing a lot of functional programming, you tend not to write all that many recursive functions. Instead, what you do is you call functions like elms or map or sum that were written recursively or could have been written recursively and you don't really care, but you're able to reason at a slightly higher level of things. But you still kind of really need to understand how to think recursively about things. Particularly because so much, there's a lot of recursive structure in programming. And kind of the nice thing about reasoning recursively is you can just really reason case-wise about things. It's like if you have a chain, how do you think about it? You have the first link of the chain, and then you have the rest of your chain. And as long as you can handle I have a link and some rest of my chain, and then I don't have any chain at all, and you get those two cases in, you can handle the entire chain.
Yeah, I mean, it's the easiest way to parse JSON.
Yeah. So hopefully everybody enjoyed that, and let me stop the screen share.